Welcome back to Chapter 2. Today we're going to be looking at Section 1, which is talking about the derivative of a function. We're going to see what this derivative thing is. And now a derivative is one of those like crazy foundational things. Like this is what a good portion of calculus is based off of. Calculus has four pieces really to it, at least high school calculus does. We have limits, which is actually what other stuff is based off of, as we'll see, and then derivatives, then integrals, which is where we take the area under the curve. We saw that in that accumulation exploration thing. And then infinite sequences and series, which Calc BC gets to, but Calc AB does not. That's really the difference in BC and AB. So derivatives is one of these big things. We're going to spend a lot of time looking at derivatives. They have crazy applications and all sorts of great stuff. So now today we get to see what is a derivative. What's it all about? We have some learning targets for the day. One, I can use the definition of a derivative to find derivatives of functions at given points. I can use the definition of derivative to find derivatives of functions. Notice the difference there was at given points versus just generally of functions. I can use graphs of functions to sketch graphs of their derivatives. So we're going to take a brief look at what it means graphically. I can use the definition of the derivative to find equations of tangent and normal lines. Now we saw equations of tangent lines at the end of last chapter. Same thing with normal lines. Interesting. I can solve applications involving the definition of the derivative of a function. So we're going to be able to use them as well. So, first piece, the definition of a derivative. Well, let's start where we left off. We left off with the slope of a tangent line. The slope of a tangent line was the limit as h goes to 0 of f of a plus h minus f of a over h. So basically, as we took these 2 points, we brought them closer and closer and closer together until they were the same point, and we found the slope between those. That's the slope of a tangent line. Well, coincidentally, that's just called a derivative. This is the definition of a derivative. It is the slope of a tangent line at that point. So we've already found derivatives. We did that last chapter. We just didn't call it a derivative. We called it the slope of a tangent line, but it is the same thing. So if we wanted to do an example using this, let's find the slope of the derivative, or find the slope of the tangent, or the derivative of f of x equals x cubed. Now, before we do that, let's take a quick look at notation here. And we're going to spend a little bit more time on notation on the next slide. But this, f and then a little apostrophe x, this is the derivative of f of x. It's pronounced f prime of x. So the derivative of f of x is f prime of x. The derivative of y is y prime. The derivative of the function g of x is g prime of x. The derivative of Optimus is Optimus prime. So it's just, we get the prime. So let's find the derivative f prime of x. It's going to be the limit as h goes to 0 of, we need to plug in x plus h. So we'll have x plus h cubed minus f of x, which is just x cubed, over h. F prime of x equals the limit as h goes to 0. X plus h cubed is not x cubed plus h cubed. We have to multiply that out. So knowing your binomial expansion really helps out in these problems. X cubed plus 3x squared h plus 3x xh squared plus h cubed minus x cubed over h. We can simplify, combine our like terms. Hey, x cubed minus x cubed, those go away. And hey, look, everything left has an h in it, just like we saw at the end of the last chapter. So we're going to factor out that h. F prime of x equals the limit as h goes to 0. We're going to factor out that h. We still have 3x squared plus 3xh plus h squared over h. We can cancel those h's, and now we can substitute in. So make all the h's 0. F prime of x equals 3x squared plus 3x times 0 is 0 plus 0 squared is 0. So f prime of x equals 3x squared. If we wanted to find it at a given point, I would still do this and then be like, all right, so f prime of 2 is going to be 3 times 2 squared. 2 squared is 4 times 3. So f prime of 2 is 12. And so that's just using the definition of a derivative to find the derivative of a function and then at a given point. Yes, you could plug that 2 in for x way up at the beginning and just deal with it that way. That works. And we saw that last chapter. I personally always find the derivative and then I plug stuff in, because chances are I'm going to have to plug in 2 for this problem. The next problem I'm going to have to plug in 5. And so I've done the work once, and that was enough. We have another definition of a derivative. It's basically the same. I mean, it's the same idea. It's the limit as x goes to a of f of x minus f of a over x minus a. It's still y minus y over x minus x as the 2 points get closer and closer together till they become the same point. It's an alternate definition. Sometimes it's easier to use. I don't use it very often, but it's good to see. So we'll do a problem like this. Let's let f of x equal root x. So we'll go f prime of a is going to be root x minus root a over x minus a. Well, if we just plug this in, we're still going to get 0 over 0. Oh, I forgot the limit. Limit as x goes to a. So if we plug in a, we're going to get 0 over 0. So we have to do something factoring here. Not going to work. I mean, technically, yes, it could work, but it's kind of weird factoring. We have roots. We're going to multiply by the conjugate. So we're going to multiply by root x plus root a. And if we do it to the numerator, we do it to the denominator. All right, now we can multiply through. F prime of a equals limit as x goes to a. When we multiply the numerator, root x times root x is x. Then we'll get a plus root ax minus root ax, cancels out, minus root a times root a is a, over, do not multiply out that denominator, x minus a times root x plus root a. And so now, x minus a's can cancel. That's that whole thing, leaving us with a 1 in the numerator. So now we can take that limit, f prime of a equals 1 over root a plus root a is going to be 2 root a. So we have 1 over 2 root a. If we wanted it at, what's f prime of 9? We get 1 over 2 root 9, which is root 9 is 3. So we get f prime of 9 would be 1 over 2 times 3 is 6. So that would be the derivative at that point using that form of the equation. So both forms, again, I prefer that form for pretty much anything I'm doing, but again, sometimes the other form comes in a little bit handy. But this is the same stuff we were doing last chapter. I don't know how much I can stress that. We've done this. We just didn't call it a derivative. Nor did we use the notation. We just kept having to say the slope of the tangent line. So, speaking of notation, let's look at some notation. There's a lot of notation for derivatives because, because it was actually developed, discovered at a few different places at about the same time. Isaac Newton discovered calculus. But we don't really use his notation much. It does have its benefits in some fairly obscure advanced topics, but we don't use it much here. But we have the notation we use, the f prime of x. That's Lagrange's notation. He also will do y prime. If we have y equals something, the derivative is y prime. M prime, anything with the prime. It's going to be that notation. That is handy when we were doing stuff like that. We're just working with equations. It's easy to use this notation. It's simple. It's that one piece as opposed to something a little bit bigger. So just working with equations, that's a great notation to use. Dy over dx is Leibniz's notation. So this one, why dy over dx? Well, we start out with, it's a slope. It's the change of y over the change of x, which we use change of y over change of x. Except that, so that's the capital delta. Except we want a really small change in y and a really small change in x. And so that changed into using the lowercase delta, which changed into using a d because it looks like a d, and that's where the d comes from, but d's are just easier. But that dy over dx, that stands for the change of y, a really small change of y, over a really small change of x. This notation is really, really nice to use when we're dealing with implicit differentiation later on. Implicit differentiation, this is hugely beneficial. We could use it just normally. If we have y, it just changes into dy over dx instead of y prime. It's just that, like, y prime is just that one thing, dy over dx, all of a sudden you have more stuff to deal with. Another way, df over dx or dw over dx, whatever the function happens to be, it doesn't have to be dy. Or we can always pull that out in front as well. So this says we have the derivative of f of x. What's nice about this is when we're defining derivatives. So if we were to use this one up here in defining a derivative, let's say a sine, we would have to say if f of x equals sine x, then f prime of x equals cosine x. That's up there. This one, we can just say d over dx of sine x equals cosine x. The derivative of sine x equals cosine x. So when we have a table of derivatives, which there's generally one in your book, either in the back or the front, I'm looking at the teacher's edition, that probably wouldn't have it. Most calculus books do actually have a table of derivatives because you get some kind of weird ones. Then you'll have several tables of integrals. But they use this one because in just one little equation, we can say the derivative of this equals this. And so that's super helpful in that capacity. So that was some on notation. And again, we use pretty much all of these throughout the year. So we just have to know that these mean derivative. Graphing. If we want to graph from the function to the derivative, so graphing the derivative from the function. Remember, the derivative is the slope of the tangent line. And so this is a bit of an art form, but the derivative is the slope of the tangent line. The very first thing I try to start with is when is it 0? We saw that it's going to be 0 here. It's going to be 0 here. That means the derivative at those points is 0. There and there. Now we need to look at the slope. On this side, we're going this way. The slope is positive, which means the graph of the derivative needs to be positive. Positive is above the axis. Now, this is a little bit tricky until you get the hang of it, because you're having to go from the slope to the y value. And it confuses people because they see it's like, well, no, but that's a negative slope. Yes, that is a negative slope, but we're not looking at the slope of the blue one. We're looking at the y value of the blue one, comparing it to the slope of the red one. So the slope of the red one is positive there, which means that the y values have to be positive. And then in the middle, we're going down, so it's negative. So it's going to go negative. We don't know how far down negative it's going to go, like how steep it's going to get there, but it's going to be negative. And then after here, it's going to be positive again. So it's becoming positive. As we saw in the first slide, we found the derivative of x cubed, and we saw that it was 3x squared. This red one here is a cubic function. The answer, or the derivative that we just graphed, is a quadratic function. So that matches with what we saw earlier. So graphing the derivative from the function, you're changing the slope of the function into the y value of the derivative. Again, it can be a bit of a mind trip until you get the hang of it, and practice is the only way of doing that. So that is the introduction on derivatives, the definition of derivatives, the fact that we've been doing this already. Oh, the tangent and normal lines. It's the same thing we were doing last chapter. Exactly the same thing we were doing last chapter. So it's the same. It's wonderful. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.